So this video is on section 1.7 or inequalities. So the first thing I want to do is figure out what is the difference between inequalities. And again, our inequalities are just our less than or greater than, less than or equal to, greater than or equal to signs. What's the difference between solving equations with inequalities and solving just regular old equations? So you've probably learned the Mongo trap. You've probably memorized that at some point in your life, but I want you to understand why we do things differently with inequalities. So this first little part is just explaining the why. So we're going to start off with this 10 is less than 20. That's a true statement. Um, so now I'm just going to add 5 to each side. Why? Because I'm the teacher and I can do anything I want. No, I'm just kidding. Because we can add the same number to both sides and it's not supposed to do anything, not supposed to change the equal mark, right? But let's see if that is true for inequalities. So when I add 5 to each side, I get 15 is less than 25. That's still true. So evidently we can add 5 or add to both sides of inequalities and nothing changes. So we can treat it just like an equal mark. Now let's see if it works for subtraction. I'm going to subtract and I get 5 is less than is less than 15. Well, that's still true. So evidently we can add and subtract to inequalities and we basically get to treat it like an equal mark. What about division? Let's divide by 5. So now we get 2 is less than 4, right? When we divide 10 by 5 and 20 by 5. Again, that's true. So evidently we can divide. What about multiply? So when we multiply 10 by 5, we get 50. Multiply 20 by 5, we get 100. 50 is less than 20. That's true. So right now, it looks like we can add, subtract, multiply, and divide, and they are all true. Okay, so right now it looks like there's nothing different from solving inequalities. There's no difference in solving inequalities and solving equal marks. Well, if that was the case, we wouldn't have a whole section on inequalities, right? We would just, at the end of an equation or equations, we'd just say, same thing works for inequalities. So there's got to be something different about inequalities. So now I'm going to divide by negative 5. So now I get negative 2 is less than negative 4. Now let's look on my number line. Negative 1. There's negative 2. There's negative 4. Notice which is the biggest. Negative 2 is the biggest, right? So my alligator is supposed to eat my big fish. But notice that my alligator right here, see my alligator? He is eating my negative 4. He's eating the little fish. So that's wrong. We can't do that. So we have to make it a true statement, we have to flip my inequality so that my alligator is now eating my negative 2. Okay. Now let's now multiply by 5, negative 5. Multiply by negative 5. And I'm going to get negative 50 is less than negative 100. So I have 0. There's my negative 50. Here's my negative 100. Which one's the biggest? My negative 50 is the biggest. Look at my alligator. See my alligator out there? What's he eating? He's eating the little number. So once again, we've got a problem. My alligator is wrong. My alligator has to be eating my biggest fish. Okay, so these are not true. These guys are no longer true. Not true, right? When we multiply or divide by a negative 5. What did we need to do to make them true? We needed to flip the inequality. So that is why you have this rule. I call it the Mongo trap because it's what everybody misses on inequalities. When you multiply and divide by a negative number, then you must flip your inequality. Remember, up here, it you can multiply and divide by a positive number all day long and nothing changes. You treat it just like an equal mark. But if you multiply or divide by a negative, you must flip the inequality. So now let's just work some problems. Okay, so these are basic Algebra 1 problems, except we have our inequality there. So I'm going to solve it for my letter, for my x. I'm going to subtract 7 on both sides. Just be careful when you subtract. Remember, I've got two negatives, so I'm not really subtracting. I'm adding those two numbers together. Okay, adding and subtracting we can do all day long, no problems, right, with inequalities. But now I'm going to divide. I'm going to divide. This time I got to divide by that -2 to get x by itself. So notice, do I flip my inequality? In this case, I do flip it because, see, I divided by a negative number. So x is greater than 6. That would be my answer. Let's look at the next part, example B. Notice I've got letters on both sides. It doesn't really matter which side you put your letter on. This time, I think I'll move my letters to the right. Okay, so I'm going to add 4x to both sides. So I'm going to get 3 is greater than or equal to 6x plus 8. And now I'm going to move my 8 to the other side by subtracting. So I'll get -5 is greater than or equal to 6x. And when I divide by 6, I get x. I get -5, 6 over here. Do I need to flip my inequality? Now notice I got a negative answer, but what did I divide by? I divided by a positive. So when you divide by a positive, you do not have to flip your side. Okay, now some of you guys might always like for your x's to be on the left when you solve it. And if you had solved it that way, if you had subtracted 2x instead of adding 4x, you would have wound up with your x. It would have you would have wound up with -6x on this side, greater than or equal to 5 on that side. Okay, and you would have divided by -6, and in that case, you still get the same answer. Notice that it doesn't matter whether the negative is on the top, the bottom, or in the middle. It's still a negative. But notice I would have had to flip my inequality. Okay, so look at these two answers. My inequalities are different. But notice that in both of them, they point to the x. They point to the x. So I call this the choo-choo train. If you have this x on the right-hand side, you will just bring it down to the left. Okay, so you'll bring down your x. And then when I choo-choo train this guy around, when I pull him around, he's going to actually turn the other direction. And then I'll bring my -5, 6 down. Okay, so when you do the choo-choo train, you're going to wind up with the exact same answer. It's just the inequality looks backwards. Okay, and when we graph these guys, as long as my letter is on the left-hand side, my graph is going to point the way that my inequality is going, and we're going to work some of those. Let's do two more. All right, regular old Algebra 1 problem, except I have an inequality, so I'm going to distribute my 2x. So I get 2x plus 14 plus 3 is greater than 2 plus 2x. All right, now I'm going to simplify. I'm going to get my my regular old numbers together, combine like terms. So I get 2x plus 17 is greater than 2 plus 2x. All right, so I'm going to get all my letters on one side. So I'm going to put my letters over here on the left-hand side. So I'm going to subtract 2x. And let's see what we have left. 17 is greater than 2. Uh-oh. What happened to my x's? Do you see that they canceled out? So I have no x's. So when you have no x's, you have two choices. You're going to look at what you wound up with at the end. 17 is greater than or equal to 2. Is that true or false? That's a true statement. Okay. So if it is true, that means it doesn't matter what you plug in to x in the beginning, because these guys are going to eventually cancel out. So it doesn't matter. You're always going to get a true statement no matter what. So basically, that means everything works. Everything works. No matter what you put in there, it's going to cancel out. So everything works. I like to say the answer is all real numbers. All real numbers. Now, my lab is going to have you write negative infinity to infinity with parentheses. This is called interval notation, which we are going to get to in this section. Okay, we're just not quite there yet. Anyway, now what happens if I had 17 is greater than or equal to 20? What if that 2 had been a 20? Well, if I get something that's false, right, that's not true, then that means this is a no solution problem. So if you get a false statement, it's no solution. But this one was all real numbers. All right, one last problem before we look at interval notation. Okay, once again, this is a rational equation because it has a fraction in it. Okay, remember, we find the least common denominator. So my least common denominator is -3 because these over here don't have a denominator. So I'm going to multiply everything by -3. Everything by -3. Each piece. So my -3's are going to cancel out, and I wind up with 5x plus 4 is, let's see, and on this side, -15x minus 12. Now let's talk about this inequality. Do I flip it or not? What did I multiply by? Do you see I multiplied by a negative? Negative. So since I multiply by a negative, I have to flip my inequality. Usually you flip your inequality at the end. Notice these other problems we've done. We flipped it at the very, very end. Well, when we did, I guess we just did one. We flip it at the end, but this one we had to flip at the beginning because we multiplied by a -1. Now I'm going to go ahead and move my 15x over to the left. Combine it with the other 5x. So I'm going to get 20x plus 4 is greater than or equal to 12. I did not have to do anything with my inequality there because I was just subtracting. Now I subtracted -4, so I get -16. And last but not least, I'm going to divide by 20. So I get x, and I'm going to go ahead and reduce that. I'm going to divide by 4, so I'm going to get -4/5. Now, what about this inequality? Do I need to flip it? Now, notice I get a negative answer, but what did I divide by? I divided by a positive number, so I'm not going to flip it. And as always, I'm going to check when I've got a fraction. I'm going to plug that into the bottom, but notice I don't have an x on the bottom, so I really don't have to worry about that. So my answer is going to be x equals -4/5. All right, now, so I want us to know how to graph these answers when we get to the end. I want us to be able to graph them. We need to be able to write them in set builder notation. We also need to be able to write them in interval notation. So let's talk about what each one of these are. Okay, so let's do our description, the verbal description. The set of real numbers greater than -3. So let's graph that. Greater than -3. So 5 would be bigger than -3. So that's going to be shaded. What about 4? 4 is bigger than -3. That's going to be shaded. What about 6? 6 would be shaded. So would 7 and 8, and so would a bazillion. So everything here, all of this is going to be shaded. So we're going to shade it all the way to the end. All right. Now let's get closer to 3. 3.5, that would be shaded. What about 3.1? That's greater. What about 3.01 or 3.000000001? So anything really to the right of 3 would be shaded, but 3 is not shaded because 3 is not greater than itself. So I'm going to put an open dot there. So my graph is going to be an open dot on 3, everything shaded to the right. Let's do the second one, and then we'll come back in and fill the set builder notation out. Okay, so the set of real numbers that's greater than or equal to 3. Notice the difference between the first one and the second one. The only difference is or equal to 3. So it's going to look exactly like what we had in the first one, but on 3, I'm going to fill that in because it is equal to. Now let's write these two in set builder notation. Set builder notation has everything written in set builder notation must have the same things in common. It's going to have a bracket, an X, and a slash. That says the set of all. Well, that basically just says the set. Sorry about that. So that one says the set, and this says of all X, and that little line right there says such that. I told you math people do not like to write. So this says the set of all X such that, and then we'll end it over here. Okay. Now we just write it with an inequality. The set of all real numbers so that the numbers are greater than 3. So that's going to be X, and we've got a 3, and it's got to be greater than 3. My alligator's eating the X, right? Alligator's eating the big fish. So the only difference between the first one and the second one is instead of having X is greater than 3, we'll have X is greater than or equal to 3. But we still have to have our bracket, our X, our slash, and our other bracket. If you want to, you can go down and put set builder notation on every one of these guys because that's what we're going to be doing in that column is set builder notation. A bracket, an X, a slash, and a bracket. And I am bracket challenged, so sometimes my brackets turn into squiggles. I try and not do that, but sometimes they do. All right, so we have set builder notation. We just have to come back in and fill it in with the actual inequality. So we're going to work all the rest of these, and then we're going to come back and talk about interval notation. Okay, the set of real numbers that are less than 5. So less than 5, so that 3 would be less than 5. Let's say 0 would be less than 5. Negative a gazillion would be less than 5. So I know I'm going to shade it to the left. Okay, 4 is less than 5. 4.9 is less than 5. Notice it doesn't have an equal mark. So on 5, we're going to have, sorry about that. On 5, we're going to have an open dot. So let's have an open dot on 5 and shade it this direction. Again, the difference between the third and the fourth one is just the fourth one says the set of all real numbers less than or equal to 5. So that one's going to have a solid dot on 5 and be shaded this way. Now notice the first two. The first two, notice these were shaded to the right, and notice that my inequalities were pointing to the right. These guys are shaded to the left, so my inequalities are going to be pointing to the left. The first one is going to be X is less than 5. Next one is less than or equal to 5. Now that only works. The shading and the inequalities point the same way. That only works when your X is on the left. Okay, so if your X is on the right, it's opposite. Okay, let's look at the next one. The set of real numbers between 3 and 5. So 4's in between 3 and 5, 3.5's in between, 4.5's in between. So we're going to shade everything in between. I call that an in-between graph. Okay. Now, notice it didn't say or equal to. There were no or equal tos. So my 3 and my 5 are going to have open dots on them. So I call this an in between graph. All right. So we're going to put my X in between a 3 and a 5. And then I've got to get my alligators eating the right fish, right? So the alligator, if it's going to be bigger than 3, it's going to eat the X. And then it's got to be less than 5, so it's going to eat the 5. All right, now this one says the set of real numbers greater than or equal to 3. Notice the or equal to is going to be greater than or equal to. You can have a solid dot on 3. So it's going to be greater than 3 or equal to it, and then less than 5. So notice it did not have an or equal to on that less than 5. So my 5 is going to have a solid dot. So that's what it looks like. So it's greater than or equal to 3, less than 5. So I'm going to do the same thing. It looks like an in-between graph, right? So I'm going to do the same thing with my inequalities in between 3 and 5. Notice that my inequalities point to the left. The 3 is the one that gets the solid dot underneath. Okay, let's look at the next one. The set of real numbers greater than 3 and less than or equal to 5. So these two say the same thing except the equals are in different places. So it's greater than 3, so not or equal to, so it's going to shade to the right of 3, and then less than or equal to 5. The or equal to gets the equal mark, gets the equal mark, also gets the shaded in 0, shaded in whole. I'm going to write it, put the X in between 3 and 5. This time my or equal to goes with the 5. And then the next one, the set of real numbers between 3 and 5 inclusive. So we know between 3 and 5 means I'm going to shade all of this in between, okay? And then again, math people do not really like a lot of words. So instead of saying the real numbers greater than or equal to 3 and less than or equal to 5, instead of having to write all that out, they just say inclusive. So that means inclusive means it includes the endpoints. So my endpoints are included. Again, I'm going to put the X between the 3 and the 5, less than signs, and both of them get the equal mark. All right, 2 left. The set of real numbers less than 3 or greater than 5. So let's talk about less than 3. So less than 3 is going to be the numbers to the left, right? So 0 is less than 3, 1's less than 3. So all of these over here, did it have an or equal to it? It did not, right? It just said less than 3. So I'm going to have an open dot on 3. Now greater than 5, so 6 will be greater than 5. So it's going to be all the numbers to the right of 5. And it did not have a or equal to, so it's going to be open dot. Notice it looks like 2 separate graphs, right? So basically, when we write it in scientific set builder notation, we're going to do the same thing. We're going to have X is less than 3, no equal to, or X is greater than 5, no equal to. All right, now one thing, we'll do one more. The set of all real numbers. Notice it didn't say less than anything, greater than anything. That's everything. Everything here. All right, so how would we write that in set builder notation? Okay, well, X is going to be in between things again, but the things are as far to the right as you can go. So how do we say as far to the right? In other words, we keep shading forever. What is the biggest number we could get to to the right. We're just going to call it infinity. And then same thing, infinity to the left, but that's a separate, different infinity. That's a negative infinity. One thing I wanted you to notice is every time that we had a less than or equal to, okay, we had a solid dot, right? So anytime you have an equal to mark, you're going to have a solid dot. Anytime you have a regular just less than or greater than, you're going to have an open dot. So let's talk about interval notation now. Okay, so from now on, whenever you solve these inequalities up here, you cannot write your answer the way that you have written it in the past, where you just say x is greater than 0. We don't do that anymore. From now on, we're going to be doing interval notation, okay? And once again, it is a shortcut way of writing your inequalities. So I want you to imagine, we're going to start with this second one. I want you to imagine that this is a railroad track, okay? And we're walking on a railroad track. Don't ever do that in real life, right? Don't walk on railroad tracks. But if we're walking in real life, and if you saw me, if you could see me, I've got my little fingers doing the walking on that railroad track. We're going to start on the left and head this way. We're going to write down the first number that we get to that is shaded. So when we go that way, the first number we get to that's shaded is my 3. So I'm going to write that down. And then I'm going to keep walking and I'm going to write the last number that we get to. Well, the last number we get to, it just goes on and on and on forever. Remember, the way we say that is infinity. Okay? So it's 3 to infinity. Now, can we ever get to infinity? Can we ever yes, I have arrived? No. Once you get to infinity, you can go one more, and that's also infinity. So you can never get there. So if you can't ever get there, you're going to put a parentheses. So all infinities and negative infinities get a parentheses. Now let's talk about my 3 right here. Is 3 a solution to this? Is 3 included? The set of real numbers greater than or equal to 3. So since it says or equal to 3, we can get to 3. 3 is an answer. So that is a bracket. So if the number is in the solution, it gets a bracket. So that's the one that have these equal marks. So if it has an equal mark, it's going to have a bracket, either a left bracket or a right bracket, or maybe both. Okay. If it does not have an equal mark, let's look at the very first one that we do. When we are walking on my railroad track, when I get to 3, I get almost to 3, but it's like 3.0000001. So it's going to look the same. The interval notation is going to look the same as this second problem, in that it's going to, I didn't mean to put a 5 there, I had to put an infinity. So it's going to have a parentheses, but that 3 is going to have a parentheses. And it has a parentheses because we can't ever get there. All right. Let's keep going. So now we're going to be walking. This time we're going to get on my railroad track. But notice the minute, and I always walk left to right. Okay. The minute I get on my railroad track, I'm shaded. So that is negative infinity. Again, we can never get to infinity, so that's going to be a parentheses. Okay. And then I'm going to keep walking until I get to 4.99999999999. Okay. So the way we say that is we're going to say 5, but we're going to put a parentheses around it. The next one is exactly the same as this one, except we have or less than equal to. We have an equal to mark. So we're going to go from negative infinity to 5. My infinity always gets the parentheses. This 5, notice it is a solid It's solid, and it has or less than equal to, and it has this equal to mark. So it gets the bracket. The in-between graph is honestly the easiest one to do because you have no infinities. Once you start walking, the first thing you're going to get to is almost 3, right? So we're going to put our 3 down, and then we're going to keep walking until we get to 4.999999. So that's going to be almost 5. I just put my parentheses on both because I'm not going to get to 3 or 5. 3 and 5 are not included in the answer. So the next 2 are exactly like what we just wrote, except my brackets are different, right? So for the next one, I'm going to hit 3. 3 is included, so I put a bracket on my 3, but 5 is not included, so I put parentheses on the 5. And then the one that says less than or equal to 5, right? We're going to have a bracket on my 5, but my parentheses gets, the 3 gets a parentheses. And then the last one, both 3 and 5 are included, so they both get brackets. All right, and then we're almost done with our interval notation. Notice that this looks like 2 separate graphs. We actually wrote it almost as 2 separate ones in our other notation, our set builder notation, right? So now we're going to do the exact same thing. This one, notice it starts at negative infinity since it's shaded to the left. So that's going to go from negative infinity to 3. My negative infinity, we always get a parentheses. What about the 3? Do you notice it has an open circle? Okay, that's because it has no or equal to. So it's going to be parentheses. We're going to skip a little space, just like we skipped here. And the next number we get to is 5, or almost 5. So we're going to go 5 to infinity. They both get parentheses. Infinity always gets parentheses. 5 gets also gets a parentheses. So I like to connect these with a U, and I call this Matthew. And I call it Matthew because it is a math U. In other words, if when you're entering it into MyLab, if you enter it in as a actual U from your keyboard, it's going to count it wrong because that's not Matthew. Okay, so I usually connect them with a U, but sometimes MyLab will ask for them to be connected with a parentheses. A comma. So just watch on MyLab Math. Just read those directions. Watch for those directions and see what it says. Okay, if it says connect with a comma and you connect with a U, it'll count it wrong, and vice versa. Okay, so you think of that as an addition. It's the left hand in addition to the right hand. All right, and then the last one is all real numbers. Everything works. So notice everything is shaded. So if we go as far as we can to the left, that's negative infinity. And as far as we can to the right is going to be positive infinity. And infinities always get parentheses. So now we know how to write our answers in interval notation. So let's come back up here and write these in interval notation. So we have x is greater than 6. If it helps, you can always graph it. So here's my 6. 6 is not included. This thing is pointing to the right. So I'm going to shade it to the right. So you can always graph it or even graph it in your mind. So I know that if I walked on that imaginary railroad track, the first thing I'm going to get to is almost 6. And I go forever to the right. So that's going to be my infinity. Infinities always get parentheses. Notice I did not have an equal to sign in my inequality, so that's going to be parentheses. So that would be my interval notation answer. Over here, now you can, I often, if it's written with the X on the right hand side, I usually do my little choo-choo train and put it on the left hand side. When it's on the left hand side, notice that it's going to shade this direction. So it's going to be from negative infinity all the way up to negative 5/6. And notice that my 5/6 has an equal mark. So it's going to get a bracket. So this would be my interval notation answer. This one, we already talked about that. All real numbers, everything worked. So that's going to be negative infinity to infinity. And the last one, again, you can draw it if you want to. There's negative 4/5, wherever that is. It's going to have a solid dot because it has an equal mark shaded to the right. So we can, as we walk on our little railroad track, I get to negative 4/5 first. Notice it has an equal mark, so it's a bracket. And then we go to forever. So that's infinity, which gets a parentheses. All right, so now we're going to work some more problems. This one, I believe that we already worked. Let me look back up there. I believe that, yep, that one is example 1B is this one. So we've already done this, example 1B. So let's do the 3-part inequality. Now I call this snakes in a pool because, do you see this snake right here? Let me make it green. We'll make it a green snake. There's my green snake. Okay, whenever a snake goes into a pool, and we used to live in a neighborhood that had a pool, and that pool happened to be next to the Middle Tiger River. And occasionally a little snake would decide it wanted cleaner water and would jump in the pool. Well, when that happens, what happens to all the people in the pool? If they're anything like my neighborhood, they would come out on all sides, right? As a mama, I did not say, no, you can't come out on this side. We all have to come out on the right-hand side. No, I just said, get out the pool. So that's what we're going to do. We're going to just get out the pool. Now, that is the snake. The X is the snake. Now, the snake's best friend is right here next to it. That's 6X. Okay, so we're going to get rid of the best friend last. All right, so we're going to, just like we would in a regular algebra problem, we're going to add 8, okay, to get it on the other side. Now, most people add it to the right-hand side, but a lot of people forget to add it to the left-hand side. That's where it's going to get out on both sides of the pool. So we're going to add 8 to all 3. That's where, this one is where most people miss it on the test. Did you hear that? On the test? Hint, hint, hint. All right. So on the left, we're going to get 9. Now, I added, right? So I don't have to change my inequality. When you add or subtract, you don't have to worry about inequalities. All right, now I'm going to divide by 6. Notice I'm dividing all the sides. Usually it's the left side, people forget. So I'm going to simplify that. I'm going to divide it all by 3. So 3 goes into 9 3 times, into 6 2 times. So 3 halves. I've got my X, and then on this side I have a 2. Notice I divided by a positive 6. So I do not have to move my inequalities. They stay the same. Okay, so this is my answer, but notice it says give the solution in interval notation. So anytime you have snakes in a pool in this class, only in Math 110, okay, but in Math 110, it's always going to be an in-between graph. I'm not going to say that it always is, but in Math 110, it's always an in-between graph. So that means I'm going to have 3 halves and a 2. right? I'm writing it in interval notation. If it helps you to, graph it, so there's 2, 3/2 is like 1/2. So the graph would look like this, right? But that just means my 3/2 is going to have a bracket because it has an equal mark, and my 2 has a bracket. So that's my answer in interval notation. Okay, so I'm going to stop this video, and we will start the next one for this section in just a minute.